Hi folks, I'm Nolan, and today I'll be presenting on groth16 recursion and some of the applications we've built over the summer using groth16 recursion. All of this work is supported by 0xPark, and most of it is joint work with the CirCom parent team, including Jonathan, Yi, and LearnChair, Adyan, Sampriti, Vivek, many of whom are in this audience. So let's get started. So I guess some people already talked about this before, but just to reiterate, what is even recursion? So in the context of SNARKs, recursion is the ability to verify a SNARK proof inside another SNARK proof. So what does this specifically mean for groth16? Given that, I guess some details about groth16 is that it uses this primitive called pairing checks, which incidentally the CirCom pairing team already had in CirCom. So we built a CirCom groth16 verifier, and using this verifier as sort of like a black box, you can build recursive SNARKs on top of this. So just to talk a little bit about how groth16 verification in CirCom works, just to give some intuition, it's basically this like groth16 verification is like this giant hairy equation, and those E functions are like the pairing functions. And essentially as a verifier, you take in as input three things. A verification key, which is some representation of your circuit, a set of public inputs, and a proof, which is some like ZK version of your witness. And you verify if this LHS equals this RHS, and then magically this proof is correct. And just to give some intuition on the other things going on here, is you can sort of think of like the G to the alpha and H to the beta terms as encoding like the wires of this circuit. I guess to be more specific, it's like, sort of like checking the outputs match the inputs if there's a wire. And similarly with the gamma and delta terms, it's ensuring that the public inputs are sort of separate of the witness, and any witness that can satisfy this circuit will work with this same amount or same set of public inputs. All right, so to do this in CirCom requires a bunch of sort of math you can jiggle around and do some stuff with. I won't go into too much detail, but you can do some pre-processing outside the SNARK and those kinds of things. But ultimately, the final result you get is that you can do a verification of a groth16 proof in a SNARK in R1CS groth16 in about 20 million constraints. This includes a couple of subgroup checks and those kinds of things. So this is sort of the final thing you get. I guess one note here is that CirCom and the SNARK.js stack is not something you can run 20 million constraints in on a client or user computer. So you have to generally stick to a remote SNARK prover kind of setup, like a beefy AWS machine or something of that sort. All right, so I guess now that we sort of have this black box of a groth16 verifier in CirCom, how can we use this to build recursive circuits? To get to that step, there's sort of two problems you have to deal with first. So first is groth16 has a circuit-specific trusted setup. What this means is that the trusted setup of a circuit has two steps, and the second phase essentially is hard-coded for the wires of the circuit itself. So that means that if you have a somewhat complex circuit where sometimes you want to verify one version of the circuit, other times you want to verify another version, each of these will need their own trusted setup. So ideally, you don't want this because there's a lot of trusted setups going on. So the solution to this is just like there's no solution. You just build self-recursive stuff. And then another sort of thing to keep in mind is that groth16 verification takes order of like number of public inputs, time, and constraints. So if you have too many public inputs, that will start dominating sort of the term, sort of the 20 million constraints term we saw previously. So ideally, you want to keep this verification low constraint and low time. So the solution, quote unquote, to this is you have this sort of general primitive or general technique of making semi-public inputs. The way I guess I like to think of semi-public inputs is like instead of, let's say you have like 50 public inputs you want to pass in. Instead, you pass these in as private inputs and expose just one hash commitment of them as a public input. And in your circuit, you verify that the hash commitment that's publicly committed matches these private inputs. And like outside this SNARK, you can do whatever you want with this public input. And this is secure in the random oracle model because you just cannot reverse like a one-way function. Oh. OK, so I guess now that I've talked a little bit about what the sort of boundaries of groth16 recursion are, it makes sense to just like think about what the mental model should be like for like an application developer, given that they have this primitive of like groth16 verifier. Generally, I like to think of this like you are sort of peeling the layers of an onion kind of thing. You have a inner circuit, for instance, which shows some statements of knowledge, let's say A1, A2, so on up to AN minus 1. And then you generate a snark proof from this circuit, which you can verify in another snark proof. So in the outer snark proof, you verify one more piece of knowledge, which let's say is AN, as well as you verify a proof of the steps A1 up to AN minus 1. So combining this, you have now a larger proof which says, yes, A1, A2, and so on up to AN are correct, and not just the previous prefix. All right, so with this, I'll talk about a couple of the applications we built this summer using this exact setup. And both of these applications point out some interesting properties of recursion or recursive ZK SNARKs in general. So first, I'll motivate Isocratia. So Isocratia is a DAO governance platform. And I guess, so currently the way usually DAO governance or any sort of decentralized voting works is like there's two sort of spectrum paradigms. One is off-chain. In this case, users just cast their votes off-chain, and then you trust like the DAO multi-sig as well as the platform to be reliable and not lie about censor anyone or do any of the weird things they can possibly do. And there's lots of platforms like this. There's Snapshot Labs, there's Sybil, there's a bunch of them. Then there's the other side of the spectrum where you have on-chain voting. In this case, voters cast their vote on-chain, which is very expensive gas because it costs gas per vote. But it's very low trust because you are only trusting a smart contract. And there's like Compound's Governor Bravo, Governor Alpha, those kinds of platforms that do this paradigm. And Isocratia allows for sort of the best of both worlds. You can do low-cost off-chain voting and also have low trust in just the contract, the ZK circuits, and the aggregators. I won't talk too much detail about how Isocratia is structured fully. You can read this slide later. But the main sort of crux of what allows Isocratia to exist is this primitive recursive SNARKs. And the idea that a aggregator can post a aggregation of all the circuits or of all the signatures from voters in one snark proof, which is fixed cost to verify on chain. So I like to think of this property as compression. It's almost like abusing SNARK's succinctness properties to the extreme. So in particular, what this circuit setup for Isocratia looks like is that an aggregator for a fixed cost on chain proves I know signatures from n voters saying no, for instance. So how does the aggregator do that in a recursive circuit setup? He first shows I know a signature from one particular voter saying no. And then he shows, oh, I also know n-1 voters saying no, except this one voter. And you'll notice that this second part is almost exactly like the original problem. So that's where recursion comes in. And you, instead of verifying all the n-1 votes individually, you just verify this like cascading sort of proofs internally. So this is compression. At least we like to think of this property as compression. And there's lots of different applications you can build that just use this property. And you also notice that this does not use the ZK properties of this at all. So in fact, we have a second property that I'll show. We think of it as composability. And in fact, we think recursive ZK SNARKs somehow are stronger than just normal SNARKs. It is slightly subtle, the difference, but typically, ZK SNARKs we think of in this context where, oh, I'm a prover, I'm showing something to a verifier, and I know this, fact or whatever it is. But with recursive SNARKs, you can actually do something that's slightly stronger, which is I can show something to a verifier without actually knowing the facts myself. So this is sort of tough to understand, but I'll just give an example of the application we built using this sort of idea. We call it ETH-DOS. These are ERDOS numbers on social graphs. And the way this works is like you have social graphs of people who say, I am your friend, kinds of relationships. And then afterwards, you can prove degree bounds. Or you can prove that, for instance, in this graph, Nolan is 4 degrees from Vitalik or something of this sort. So how does this sort of setup work? Vitalik sends, let's say, a signature proof to alice.eth, who Alice sends it to a Bob, Bob sends it to Adhyan, Adhyan sends it to Nolan. So what does this sending relationship mean? So I can get a signature from Adhyan saying that I am his friend, and then I will prove that I know Adhyan is 3 degrees away from Vitalik, and I am a friend of Adhyan, and therefore I am 4 degrees from Vitalik. And Adhyan himself has the same proof cascading down. So we generally like to think of this property as composability, because now I do not know the path between me and Vitalik myself, but I am able to make claims about this path to outside world as well as myself. Yeah, that's all. We'll have a blog post on groth16 recursion coming out soon, as well as hopefully Isocratia and EDOS will release soon.
All right, any questions for Nolan?
You say, so you're aggregating the votes by recursion. Can you say how that would compare? How does that compare to just verifying all the votes like in one giant circuit?
Right. So with groth16 in particular, we wanted to use ECDSA signatures for voting to be like maximally compatible with existing solutions. A single ECDSA verification is about 1.5 million constraints, and one recursion is about 20 million constraints. So in theory, and I think the largest trusted setup go on the order of like 100 million. So in theory, you cannot verify more than 100 or so votes on a single like ECDSA repeated inside a SNARK circuit setup. But with Isocratia kinds of setup, you can verify essentially infinite votes.
Yeah. So it's for the So basically, it's the recursion gives you the scalability property you want.
Exactly. Yeah.
Makes sense. Thanks.
Have you considered maybe verifying SNARK pack inside a circuit rather than each of the individual groth16 circuits? That sounds like something that would be faster if you're aggregating many things.
Right. I guess we definitely looked at it and we tried to understand it, but our conclusion was it's quite quite hard to understand. So we sort of gave up on that.
We can help.
Yeah.
On the aggregation for the voting, how do you make sure that 2 people do not aggregate the same vote? Like, how do you make sure this, aggregations are unique?
Right. So that double counting problem is one of the things I sort of glossed over. But yeah, hopefully the blog will have more detail. But essentially, you can do some tricks with vector commitments where you don't allow someone to like include the same vote or the same like Merkle root again and again kind of thing.
Ah, cool.
Yeah.
Probably there is some resource online, right?
Not yet, but there's drafts.
I really like the 2 examples because I think they're different enough. Like ETH-DOS, each proof really builds on the previous proof, whereas when you're aggregating votes, it doesn't matter how you order them. So I guess like for the voting for Isocratia, you could also look into Gemini. If like all you're using the recursion for is to reduce prover space complexity, Gemini, our streaming prover, also does that.
Right, for sure. I think one of the biggest things with like doing this project in the first place, it's kind of ridiculous to do this, but the biggest reason I think to do this is like we have a lot of like dev tooling kinds of support for Circom, SNARK.js, and all of these things. So it's somehow easier to do this than write your own proving system from scratch or implement SNARK pack.
Cool. Oh, wait, one more question. Oh, never mind. I thought I saw someone. Anyways, let's thank Nolan.